So in this problem we have a uniform rod of mass big M and length big L, which is attached to an axle and allowed to rotate horizontally without friction. And there's also a bead of mass little m, which is fixed initially at a distance d from the axle, and the rod bead system is initially rotating with an angular velocity of omega naught. Now the bead is then released and allowed to slide without friction along the rod. And in part A of the problem, we're asked to figure out which quantities of the bead rod system are conserved. Now notice that the axle can exert forces on the bead rod system, which means that the net external force on the system is non-zero. Since an external force on a system causes a change in momentum in the system, this means that momentum is not conserved. However, the forces from the axle on the system do not exert any torque about the axle, and gravity also does not exert any torque about the axle on the system, since gravity acts downwards and our system is rotating in the horizontal plane. Therefore, angular momentum must be conserved, since the net torque on the system is zero. Also notice that the bead is allowed to slide along the rod without friction, and the rod is allowed to rotate without friction, which means that kinetic energy is also conserved. So these are our two quantities that are conserved in our bead rod system. Now, part B of the problem, we're asked to figure out what final angular velocity is of the bead when it reaches the end of the rod. Now we can use conservation of angular momentum in our system to figure out what the final angular velocity of our system is going to be. So let's start off by noting that the initial angular momentum of our system is equal to its final angular momentum, since we determined that angular momentum is conserved. So we're going to take our initial angular momentum to be when the bead is initially a distance d from the axle. So remember that angular momentum is the moment of inertia multiplied by the angular velocity. So we're going to sum up the angular momentums of the rod and the bead. So for the bead, we have the moment of inertia is just little m times d squared, and angular velocity is omega naught. Now for a uniform rod that is rotated about its endpoint, the moment of inertia is going to be given by 1/3 big M big L squared times omega naught. Now if we sub in for little m and d, we get that this term, we have little m is big M over 3 and d is big L over 3. So md squared omega naught is just going to be 1 over 27 times big M big L squared omega naught plus 1 over 3 big M big L squared omega naught. So that's just going to be 10 over 27 big M big L squared omega naught. Now the system's final angular momentum when the bead is at the end of the rod is going to be the moment of inertia of the bead, which is m times big L squared omega naught, or not omega naught, times its new angular velocity omega, plus 1/3 big M big L squared times omega. So omega is the final angular velocity of the system when the bead is at the end of the rod. So simplifying this, we have that little m is big M over 3. So this is 1 over 3 L squared omega plus 1 over 3. There's a big M here. let's actually just make this cleaner. 1/3 big M L squared omega plus 1/3 big M L squared omega. Simplify this down to 2/3 big M L squared omega. So since we know that the initial angular momentum of the system is equal to its final angular momentum, we can equate these two equations and get that 10/27 big M L squared omega naught is equal to 2/3 big M L squared omega. So the M L squares cancel out on both sides. If you multiply by 3/2, we get that omega is equal to 3/2 times 10/27 omega naught, which simplifies to 5/9 omega naught. So that's the angular velocity of the bead rod system when the bead is at the end of the rod, which means it's also the angular velocity of the bead when it reaches the end of the rod. Now, part C of the problem, we're asked to find the tangential velocity of the bead when it reaches the end of the rod. So we know its angular velocity, omega. So its tangential velocity is just going to be given by omega times its distance from the axle, which is going to be big L when it's at the end of the rod. So our answer for part C is going to be 5/9 omega naught times big L. Now part D of the problem, we're asked to find the speed of the bead when it's at the end of the rod. So to do this, we're going to use conservation of kinetic energy instead. So we know that from part A, the initial kinetic energy of the system is equal to final kinetic energy of the system. We're going to take initial to be the bead when it's at distance d from the axle, and its final to be when the bead is at the end of the rod. So let's figure out what its initial kinetic energy is. The kinetic energy of the system is going to be the sum of the kinetic energies of the bead and the rod. So for the bead, it's going to be half of its moment of inertia, md squared, times its angular velocity squared, so omega naught squared. And similarly, for the rod, it's going to be half of the moment of inertia for the rod, which is going to be 1/3 ml squared times its angular velocity omega naught squared. So subbing in for m and d, we're going to get, this simplifies down to 1/2 big M big L squared omega naught squared. And in brackets, we're going to have a factor of 1/27 plus 1/3. Now this is just going to be 10/27. So we have half times 10/27 big M L squared omega naught squared. Cool. So now we can figure out what the final kinetic energy of the system is. So in the same way, we're going to add up the kinetic energies of the bead and the rod. So this time for the bead, we're going to use half times little m times its velocity, v, or its speed, v squared, plus the kinetic energy of the rod, which is half times big M/3 big L squared times omega squared. Now, if we sub in for m and our value for omega, which we found in part B, we're going to get 1/2. Let's move this up. So 1/2 big M/3 v squared plus half of, well, omega is just 5 over 9 omega naught, so we have 5 over 27, and it's omega squared. So since omega is 5 over 9 omega naught, omega squared is 25 over 81 omega naught. So this is going to be m over 3 L squared and 25 over 81 omega naught. So now we can equate these two equations and get that 1/2 times 10 over 27 big M, big L squared, omega naught squared is going to be equal to 1/2 big M over 3 B squared plus 1/2 big M over 3 L squared times 25 over 81 omega naught. So we're going to write this as 10 over 9 M over 3, so we can clearly see that we can cancel out the 1/2 and the big M over 3, as well as not the L squared. Alright. So now, if we group all the omega naughts to one side and isolate for B squared, we get that B squared is equal to 25 over 81 big L squared omega naught squared minus, should be a minus because we're moving this to that side. So minus 25 over 81 L squared omega naught squared plus 10 over 9 L squared omega naught squared. So that's going to come out to be, we multiply that by 9, get 90 minus 25, which is 65. So 65 over 81 L squared omega naught squared. Which means that our answer for the speed of the bead when it's at the end of the rod is going to be the square root of 65 over 9 times omega naught times big L. So that's our final answer for part D of the problem.